Good afternoon, everyone. I'm really honored to be here today and to share my research with you. My name is Firuja Tasneem, and I'm an undergraduate student from the Department of Computer Science Engineering in Dhaka, Bangladesh. The title of my research is an integrated BIM, ABM, SDANN framework for predicting occupant thermal comfort in climate resilient urban landscapes. In this presentation, I will discuss how digital modeling and artificial intelligence can work together to predict outdoor thermal comfort, especially in climate vulnerable cities like Dhaka. Here is a quick overview of what I will be covering today. First, I will start with the background and problem statement explaining why outdoor thermal comfort. These are the table of contents that I will be sharing. First, I will start with the background and problem statement, then the rationale of this research, the methodology, key findings, research contribution, and at last the conclusion and maybe some future works. So let's start with the background. Thermal comfort is the how comfortable people feel with the temperature around them. It is a key factor in designing sustainable outdoor spaces, especially in dense and warm cities like Dhaka. This outdoor comfort affects how people use public spaces, like their mood, their productivity, and overall urban livability. However, as cities become more crowded and temperatures rise due to the urban heat island effect, maintaining this outdoor comfort has become a serious challenge for us. And the problem is that the most traditional models they focus mainly on indoor environments. They often fail to capture the complex interactions between the environment, the human behavior, and built infrastructure altogether. And all of these vary dynamically in the outdoor areas. Because of this limitation, there is a need for dynamic integrated framework that can simulate and predict how people can actually experience comfort in real and changing urban conditions. So the main rationale behind the study was to build a robust integrated framework that can accurately predict occupant comfort in complex outdoor environments because this would allow urban planners and designers to make evidence-based decisions for more climate resilient and human-centered urban designs. From this rationale, we have two main objectives. The first one is to develop a VIM, AVM, SDANN framework for predicting outdoor thermal comfort, and the second one is to calibrate and validate this model with real-world data so that the predictions would be reliable and meaningful for practical applications. So we basically wanted to bring together digital modeling, human behavior simulation, and AI into one workflow that would support sustainable design of these outdoor spaces. Now, moving on to the methodology, this framework actually has four parts or four layers. The first one is BIM or Building Information Modeling, which represents the urban infrastructure like buildings, open spaces, and the vegetation. ABM or agent-based modeling, this represents human behavior such as movement patterns and space usage. Then the SD or system dynamics, this tool models dynamic environment parameters like temperature, humidity, carbon dioxide, and this varies over time. And finally, the ANN or the artificial neural network, this is used to predict the thermal comfort by learning from the data. So in one line, the BIM builds the physical world, ABM adds human interactions, SG introduces environmental dynamics, and ANN learns the comfort patterns. Together, these form a hybrid framework which is capable of what I was saying is that ABM or the agent-based modeling represents the human behavior, such as the movement patterns, or system dynamics models the dynamic environments, and ANN, the artificial neural network, is used to predict thermal comfort. So, in one sentence, the BIM builds the physical world, ABM adds human interactions, SD introduces the environmental dynamics, and ANN learns the comfort pattern. So this is how we actually generated the data. In step one, we generated the synthetic data using BIM integrated ABM and AUT models. These simulations represented how occupants might behave under different outdoor conditions. For example, varying shade, surface types, and crowd density. In step two, we collected real world data from four outdoor urban spaces within a university campus in Dhaka. The outdoor spaces, you can see this in this picture. The first chosen landscape was the field in front of the Market Tower. The second one was the field beside the canteen. The third one was the academic building front. And the fourth one was the playground near the mosque. All these four sites we have noticed had different characteristics like tree cover, building density, and exposure to sunlight, which ensured a very diverse condition. And from these sites, we collected a total of 1,000 data samples through systematic field surveys, also through sensors in summer season of this year. Each of these data record included 14 features. All these features are listed here. We had environmental features, demographic features, spatial features, and human perception. For demographic features, we had age and gender, etc. For environmental features, there were temperature, humidity, carbon dioxide. For spatial features, there were surface types, and then we had a participant subjective thermal comfort survey. So, if I explain about the data collection process, at first we came up with these 14 features, and then we made a Google form to collect the survey data from the people because we included both quantitative and qualitative data in our features. That's why it was important to collect the occupants' real reaction or the occupants' actual comfort level. And also, we used a few sensors like air quality indicator and lux meter to measure some of these environmental data. And after that, we cleaned those data, removed outliers, and after that, we started our calibration. So in calibration stage, we performed model calibration. The synthetic data set from the simulation models was calibrated with the 1,000 real world observations that we have collected. And to evaluate this calibration accuracy, we used CVRMEC, the coefficient of variation of the root mean square error, and the MBE, the mean bias error, following the ASHRAE guidelines. And the next step, we developed and trained an ANN, more specifically, and a feed-forward neural network model using the integrated and calibrated data. And at last step, we evaluated the performance of the ANN using MSC and RMSC, which is the mean square error and root mean square error. If you notice in the key findings, the integrated framework that we have built with BIM, ABM, SD, and ANN model, this BIM, ABM, SD model achieved really strong agreement with the real world measurements because the CVRMC values range from 24.37 to 27.7%, where the standard threshold was it has to be less than 30%, and for the MBE, it was plus minus 10%. And if you look at the ANN prediction, the accuracy of the artificial neural network model was more than 80% with a MSC value of 0.9 and RMSC value of 0.95. And these findings indicated that the feed-forward neural network model could effectively learn and predict occupant thermal comfort from the integrated dataset. If I talk about the contribution of this research, it has both methodological and practical contributions. From a practical standpoint, this framework provides decision support for architects, urban planners, and policymakers. It allows them to virtually test different design strategies such as increasing tree cover or hanging pavement materials and immediately see the impact on human comfort. And from a methodological perspective, it introduces a new integrated modeling approach that combines four domains: digital, construction, human simulation, environmental dynamics, and deep learning. So, in a city like Dhaka, where unplanned urban growth often reduces livability, such predictive tools are especially valuable for designing climate adaptive, human centered outdoor environments. To conclude my presentation, I would like to say that this study developed and validated an integrated BIM, ABM, SD, and ANN framework that can effectively predict occupant thermal comfort in outdoor urban landscapes. And this model, the model that we have made with FFNN, it achieved a strong calibration performance and high prediction accuracy, showing that the FFNN can predict very effectively. Also, the results meet the ASHRAE validation standards because uh, the ASHRAE validation was 30% and we had up to 24.7%, which actually validates our model. So when the artificial neural network model was trained with this calibrated data set, we saw that it also had a very good accuracy. So in conclusion, I can say that our predictive model worked, the framework that we have built performed really well. In future work, we plan to enhance the framework by including additional behavioral and environmental factors as window flow, wind flow, clothing insulation, and activity level, and test it in other cities. We can test it in other cities or other different types of buildings so that we can evaluate cross-regional applicability. Thank you so much for your attention. I would be happy to take any questions.